This is A23 Physics 6 June 2006, and this again is a synoptic question, and it's question 5. And the first part of the question was on motion. It says graphs in physics. You will have met graphs throughout your study of physics. In the theoretical part of the subject, they are used to show the relation between variables, to illustrate principles, and to present data. In practical work, you will have used graphs extensively in the analysis of your experimental results. Part A, B and C of this question are about graphs which are familiar from your theoretical work, and Part D is on the practical applications of graphs. Part A, Figure 5.1 shows the speed v of a particle moving in a straight line and how it depends on time. So you can see that it's a graph with a constant gradient. And you can see there that it's constant if I put the ruler down. Describe the motion of the particle. So it's a VT graph which is a constant gradient, and that means that you have an object which is starting from rest, and then it's going to move with a constant acceleration. Now the two marks there, it's not that obvious that you would write starting from rest, but do put that in, because that will really help, and it'll make sure that you're getting your 2 marks there whenever you need them. On figure 2.2, sketch a graph to show how the acceleration of the particle depends on time t. So we know that the acceleration is constant, we can tell from the last graph. So it just has a constant value, and therefore we're just going to draw a straight line across, constant value, like that. On figure 5.3, sketch a graph to show how the displacement s of the particle depends on time t. At time t equals 0, the displacement is 0, so you're going to start at 0 here. Now, displacement time, if you have a constant acceleration, then after 1 second your velocity will have increased by a certain amount, and after 2 seconds will have increased by the same amount, and so on. But that means in each second your distance that the object travels will be a little bit further. So it will travel a small distance in the first second, but in the second second it will be larger, and the third second it will be larger again. And so your graph is a curve like that, and it's an upward curve. This is the same question, it's part B, and this is a waves question. Figure 5.4 shows 2 sine waves A and B. These waves are superposed to give wave C, and wave C is at the bottom here. Take measurements from the graph at time t equals 0.8 seconds, 8 seconds, and use them to confirm that the principle of superposition of waves has been applied correctly to give wave C. Show your reasoning. So we need to look at 8 seconds here and read off a value for A and for B. Okay, so for A, I'll just write it beside it so that you can see this. For A, the value there is a positive number, and it is roughly, I'm going to write a plus there, 0.8 centimetres. For B, you can see at 8 seconds that it's minus 1, minus 1.6, minus 1.7. And for C, we'll have a look at 8 seconds. C is roughly minus 0.9 centimetres. So what we're going to do is add A and B and hope that we get the value that we have there for C. So if we add A plus B, should give us C. So A is plus 0.8, B is minus 1.7, and when you do add those two together, you do get minus 0.9. So the reasoning is, with superposition, the total displacement of the resultant wave equals the sum of displacements of the individual waves. Part 2, determine the amplitude and frequency of wave C. So if we go back to wave C, the amplitude there is obviously from the rest position to the maximum displacement, and that's roughly 1.7 centimetres. So we'll just write that down, 1.7 centimetres. And then the frequency, we have to determine the time period first. And you can tell there that there's one complete wave, and that takes 6 seconds roughly. So one time period equals 6 seconds, and then frequency is 1 over t, which is 1 over 6 there, and that gives you 0.17 hertz. The amplitude of wave C is not equal to the sum of the amplitudes of waves A and B. Explain why this does not contradict the principle of superposition. So the amplitude of wave C is not equal to the sum of amplitudes. So that would imply that you're just adding that amplitude and this amplitude. But the problem is that they're not in phase with each other. Yes, if they were in phase with each other, you could add those two and get a total amplitude, or add this one and another trough from A and get a total amplitude. But that's not the case. So that's what the problem is. So it doesn't contradict, as A and B not in phase with each other. It would be true if A and B in phase. Part C of the question is a capacitor question.